So in the last lecture, I gave you an overview of how we parallelize finite element computations on, let's say, multiple processors when you want to use distributed memory. Typically, we would use MPI for this. And I gave you an idea of, let's say, the steps that are necessary. You have to distribute the mesh. You have to distribute the linear system, for example. And we looked at step 40 that actually uses this in practice. So what I would like to do in this lecture is give you a little bit of an overview of, let's say, the technology that sits behind how we solve linear systems in parallel computations. And part of that will be that I give you an idea of, let's say, the historical context in which these methods were developed and what works and what doesn't. Clearly, many of the pieces of software that we use to solve linear systems on, let's say, very large systems, let's say thousands, tens of thousands, hundreds of thousands of processors. There's a lot of software infrastructure behind that is so complicated that I don't really want to go into any kind of detail. But I want to give you, let's say, the spirit, the thought process that's behind this when we design the software and for you to get an idea of what works and what does not. So this is lecture 41.75. And now it's about parallel solvers and preconditioners. So historically, there have been basically three fundamental approaches of how you could solve problems on parallel computers when you want to solve a PDE numerically. So the first one is domain decomposition, and I'm going to give you a few examples and give you a little bit of the overview of this in the next few slides. The basic idea is that in domain decomposition, you split the domain into smaller pieces. You discretize the PDE on each one of these subdomains, and then you somehow need to come to some conclusion. Let's say you need to iterate out the solution of the subdomains. And I'm going to show you how that works and also why that doesn't work very well, why we largely have moved away from these. An alternative is what I would call global solvers, and that's what we use in deal.II, and that's what most of the other packages today use that solve on very large systems. Global solvers essentially discretize the whole problem on the entire domain, and what you get is one very large linear system, potentially very, very large. So we've solved problems with more than 1 billion unknowns, which today still is pretty large. And then you somehow have to come up with a linear solver and a preconditioner to solve these very large linear systems in parallel. There's a third alternative that, let's say, intellectually I personally find the most satisfying. It's called the mortar method. The mortar method essentially thinks of the PDE as a whole, but still splits the domain into individual blocks and then solves a global system where the individual blocks are coupled by Lagrange multipliers. I personally find that a beautiful method. I have a penchant for optimization theory, and what you do in the mortar method is you define Lagrange multipliers for constraints, and I find that really elegant. I'm not going to go into detail. The technology for this is a little bit complicated, and let's say the mathematical formulation and to understand what the mathematics behind it is a little bit more complicated than the other two methods. And it suffers many of the drawbacks that I'm going to discuss with the domain decomposition method. So I just want to throw out there that there's sort of a compromise between domain decomposition and global solvers that avoid some of the pitfalls of domain decomposition and retain some of the strengths of global solvers. But like I say, I'm not going to go into it. I think ultimately the downsides of the mortar method outweigh the benefits, and like I alluded to, most of the codes today use global solvers. So let's take a look at this. So historically, there was an idea that came around in the 1870s by Mr. Schwartz, in which he wanted to solve a problem like this. So let's say you have a domain that looks like this. It consists of a circle and some sort of rectangle that goes with it. And if you've taken a basic PDE course, you know that we know analytically how to solve PDEs on circles and on rectangles. It's not very difficult to do this. We can write down the solution as a series expansion, for example. So What Schwartz said is essentially this. So if I want to solve a problem on a domain like this, of course I can't write down the exact solution. There is no series representation of the solution on this domain because I typically can't write down the eigenfunctions of, let's say, the Laplace operator, for example. So what he suggested back in the 1870s, so this was long before numerical methods came along, certainly long before computers were there, is essentially like this. So let's say you start with solving the PDE on the circle. And the boundary values that you would have to choose on the circle are, well, they're given on this part here, on the outer part. And on this part, well, we don't know the boundary values, of course, because we only know the boundary values over here. So on this part here, choose whatever you want. Okay? So we solve the PDE on the circle with arbitrary boundary values here, and we get a solution that we call U1 that lives on the circle. The second part would be you solve the PDE on the rectangle. And on this part out here, we know the exact boundary values. And on the values over here, or on this part of the boundary of the rectangle, we just use U1, the previously computed solution on that circle here. Okay, so we have values all the way around. It's a rectangle. We can solve exactly. We know we have a series representation and so on and so forth. That gives us a solution U2 that now lives on this rectangle. Okay, and then we can iterate this. So we go back to the circle. We take the exact boundary values that we know out on this part here, and on this part of the circle, we take as boundary values U2, the solution that we just computed. Okay, so we go back and forth, and Schwartz did this. I think it's miraculous that back in the day they would do these sort of things. He did it on a piece of paper, right? It took 80 years until Michelin came along, and so Schwartz was German, Michelin was Russian, until he proved convergence. So we know today that this iteration doesn't just work empirically, but it actually converges. So that's sort of the historical background of this method. This is called the alternating Schwartz method. And of course, you can do this on a piece of paper, or today you can do this on a computer. So on a computer, you would just solve the PDE on the circle and on the box numerically. And you would do the same things that, well, you start on the circle, you choose arbitrary boundary values here. You solve on the box where you choose the previous solution of the circle on this part of the boundary value, and then you just go back and forth. When you do it on a computer in discretized form, the shape of the subdomains is no longer important, right? To Schwartz, it mattered because he needed subdomains for which he knows the exact solution, for which he can compute the exact solution in some, let's say, in a series representation. To us today, that doesn't matter anymore. Of course, in addition to this, the, let's say, number of subdomains does not matter to a computer. We can have as many subdomains as we want, and in particular, if you have some domain that you want to solve a PDE on, you just split it into different blocks that overlap. They could be circles, they could be boxes, they could be potato-shaped or whatever shape you want. And then you just solve on this block, you get a solution. You take the next overlapping block, and you take the boundary values that you just computed, and you just keep going back and forth. So all you need is that you can split your domain into subdomains on which you can solve PDEs numerically, and these subdomains need to overlap. We call this today the overlapping domain decomposition method, and the name alternating Schwartz has stuck. So we recognize the name Schwartz in numerical methods today as something that is domain decomposition. You can do an alternative to this. So let's say you don't want to mesh something with overlapping subdomains, but because that seems to suggest that you need to do some work multiple times. But let's say you would want to have a method where you just split your domain into non-overlapping disjoint subdomains. Okay, so like this picture here. So let's say you would have a subdomain here. It has a boundary, and the boundary is exactly the boundary of the other subdomains around it. So in a case like this, you might think, well, I can do the same thing again, right? Let's say I start solving on the blue subdomain here. Okay, I'm going to take the exact boundary values of my PDE on the outer boundary. I'm going to choose arbitrary values here on this circle. Okay, I get a solution on the blue subdomain, and then I move on to, let's say, the yellow subdomain. And on the yellow subdomain, well, I'm going to choose arbitrary boundary values here and here and here, because I don't know anything about it yet. And over here, well, I'm going to choose the Dirichlet values of the blue solution as the Dirichlet values of the yellow problem. Okay, and I keep doing this, and I iterate, and you will quickly realize this does not work. The reason being that, well, so I chose arbitrary Dirichlet values on the circle for the blue solution. Okay, for example, let's say I chose 0 boundary values. Okay, so if I choose 0 boundary values, 0 Dirichlet boundary values for the blue solution on the circle, then obviously U1, my solution of this problem, is going to be 0 on that circle here. Okay. Now, if I take these 0 boundary values as the boundary values for U2, the solution on the yellow subdomain, well, I will get 0 boundary values here as well. Okay, and I keep doing this, and at the end, after n iterations, I go back to subdomain 1, and I use the boundary values of all of the subdomains that are computed on as boundary values for the blue one. Well, but because I use 0 boundary values here for the yellow subdomain, I still have 0 values. So I have not made any progress, right? So if you go back here, that was not so much of a problem, because let's say I start with the 0 boundary values here to compute on the circle. Okay, so the red solution is 0 here, but it is going to be non-zero over here. Okay, and then when I solve the blue solution, well, the blue solution will give me something. In particular, it will likely give me something that is non-zero here. So in the next iteration, the boundary values I have here are probably closer to the exact solution. So the boundary values for the circle are probably going to be closer to the exact solution than they were before. And so this overlapping thing helps me get closer and closer. Whereas here, if I only ever take Dirichlet values, I'm not making any progress. I will have the same boundary values in every iteration. So if you only work with Dirichlet values, that doesn't work. What you need to do is, let's say, you solve something that is called the Dirichlet-Neumann iteration. So let's say I solve on every subdomain once with 0 Dirichlet values. Okay. But then the next time around, when I come to to solve on the blue subdomain the second time, I'm not going to use Dirichlet values here, but I'm going to use the Neumann values of the yellow solution. So I'm going to say that du over dn of the blue subdomain equals du over dn of the yellow subdomain. Okay, where n in this case always points in the direction outward of the blue subdomain, for example. So I'm using a different aspect than the one that I put in. So I put in Dirichlet values and I get out Neumann values, and in the next iteration I use the Neumann values from the subdomain to impose boundary values on the blue one. Okay, so if you iterate this back and forth, then that can work. So this is what the Dirichlet-Neumann iteration does. It's a non-overlapping domain decomposition method. So if you look at this from, let's say, history's perspective, you can ask, okay, so this is what we did in the 1870s and what Michelin still did in the 1950s, and but does this work? And the answer is, well, so let's say when people started to do parallel computations, maybe in the late 80s, certainly in the 90s, in the early 2000s, that was the method that everybody was thinking is the way to go. And so in those days, let's say you take your domain, you put a more or less uniform mesh over it, and then you would split it up into overlapping subdomains, and you iterate it out. And this works, sort of. There was certainly a lot of developments that go beyond just the simple methods that I showed you, let's say the Dirichlet overlapping method, or the Dirichlet-Neumann non-overlapping method. There are many other methods that came out of this that work reasonably well, But in practice, the answer is that it converges too slowly. So the downsides that we have are certainly that the iteration converges not nearly quick enough, and in particular, the thing that makes it awkward is that the number of iterations that I need to do to get close to the solution grows with the number of subdomains that I have. And that's actually quite easy to understand, because if you think of this picture, for example, let's say I'm solving the blue subdomain with 0 boundary values, okay, and then I'm going to solve all of the other ones. So in every iteration, I move information, let's say, from this subdomain to this one, from this one to this one, from this one to this one. So there is something like a distance. How many iterations does it take to get from one end of the domain to the other end of the domain? Because in every step, I can only move from one subdomain to the next subdomain. And so if you have, like in this picture, I don't know, maybe half a dozen or maybe a dozen different subdomains. Actually, how many is it? It's 4, 8, it's 10. Okay, so if you have 10 subdomains, we know that it will not take more than 10 iterations for information to get from one subdomain to any other. Okay, but if you have a processor or a machine with, let's say, 1,000 processors, then it might take a large number of iterations for information to get from one end to the other end of the subdomain. And clearly, the overall iteration cannot converge faster than this. So these Schwartz methods, these domain decomposition methods, are good when you have 10 or 50 processors. They're not very good anymore when you have 1,000 or 10,000 processors, simply because the overall number of iterations is too large. Okay. So this is something that applies even if you do not parallelize it. So I haven't talked about parallelization. When you want to parallelize this, of course, what you would do is you would solve, let's say, every processor has one of these subdomains, and in every step, every processor solves the PDE on its own subdomain, and then communicates its boundary values to the neighboring processors. Okay, so we can parallelize this. Every time you solve something, you just use the most recent boundary values you get from the other processors. So that's sort of the way we would parallelize it. But like I say, if you have a large number of subdomains, the overall number of iterations you need is just too large. It does not work very well. There's one argument, I think, that really sounded the death knell to domain decomposition methods. Namely, if you think about how we solve PDEs today, you would want to have, let's say, an adaptive mesh. You would want to refine the mesh adaptively. If something's going on over here, if there's a singularity, you would want to refine over here. So what that leads to is that, let's say, in the beginning, you have a uniform mesh, and let's say you have 10 processors, so you split up your domain into 10 roughly equally sized chunks. Okay, they all of these subdomains have roughly the same, let's say, geometric size, and if your mesh is uniform, then the number of cells you have in every subdomain is also roughly the same. So when you think about this parallel iteration where everybody solves their own PDE on their subdomain and then communicates the boundary values to the other processors, that works reasonably well if it takes roughly the same amount of time to solve this subdomain's problem and this subdomain's problem. But now let's say there's a corner singularity over here. So you want to refine the mesh over here, and suddenly the subdomain and the processor that owns it have 10 times as many cells as the one over here. So in every iteration, this one does some work and, oh, it's done. But this one here has to work so much harder because it has 10 times as many cells. So it takes 10 times as long to solve this subdomain than this one here. And of course, in the other 90% of the time, this processor is just going to sit there and twiddle its thumb and do nothing. If you have, 2 or 3 or 4 processors, you can tolerate if a few of these processors are idle. But if you have 1,000 processors and 950 of these are idle 90% of the time, that is not acceptable. I mean, that's not a good use of your resources. So when you have large numbers of processors, what you really need to achieve is something that we call load balancing. So load balancing means that every processor has about the same amount of work to do. Now, in the domain decomposition method, that would mean that if we refine this subdomain a little bit, that we would have to achieve that we shrink this subdomain and we grow subdomains elsewhere so that they all have roughly the same amount of work. So you suddenly have to move meshes around and so on and so forth. And that just becomes really awkward to implement something like this. So in practice, load balancing is difficult if you don't have something like a global mesh that meshes the whole thing and you split it up in every mesh refinement iteration. Now, if you already have a global mesh, then what I'm going to show you next means that you don't have to do domain decomposition. Domain decomposition really works at the level of the PDE. You take the domain and you split it up, and then you discretize each one of these subdomains individually. But then you can't load balance, right? Because you split the domain independent of any mesh. The opposite view is that you start with a mesh that covers the entire subdomain, and you split the mesh in such a way that every processor has roughly the same number of cells. So that's what I'm going to show you next. This is what we call global solvers. Okay, so global solvers essentially means you cover the entire domain in one mesh. And this mesh might have a lot of cells, right? I mean, we've done computations where meshes have, let's say, billions of cells. Okay. So I might not be able to store the whole mesh on any processor, but let's say conceptually, the entirety of all of the processors have one data structure that might be distributed among many processors that actually stores the whole mesh. And then what we need to do is we need to partition the mesh. So partitioning the mesh means that, well, we split it into chunks so that every processor has roughly the same number of cells. But as I say, conceptually, it is still one mesh. Then what we do is every processor discretizes its part of the domain. So in other words, it assigns degrees of freedom to the cells that it owns. But we still think of it as a whole. So degrees of freedom are enumerated not from 0 to n on every single processor, but let's say from 0 to n on processor 1, and from n to 2n on processor 2, and from 2n plus 1 to 3n on processor 3, and so on and so forth. Okay, so it's all part of the whole. What you get out of this is one very large linear system, possibly billions of unknowns. Okay, and for problems of this size, you understand that we typically cannot use direct solvers, or at least not easily. So you want to use an iterative solver, and if you want to use an iterative solver, you need to have a preconditioner for it that applies to the whole big linear system. Okay, and I'm going to talk about these parts. When you want to adapt the mesh, then you're going to refine some cells over here, maybe not refine over here. So the overall number of cells grows, and let's say the process in which we typically do this is, let's say every processor owns a number of cells. You refine the cells that this processor owns. Now there's an imbalance. This processor has many more cells than this one. So you need to rebalance this data structure that stores the whole mesh. So in the way we typically implement this is that this processor will just give some cells to the neighboring processors, and if they still have too many, then they move some of their own to neighboring processors. So in essence, the whole number of cells is always subdivided in such a way that that every processor has the same number of cells. That's what we call rebalance after mesh refinement. Okay, so that's clearly a computational challenge. It's not easy to implement this. There's going to be a lot of communication between these processors when one processor wants to give cells to another one. But it is feasible to do this. So the point simply being is that, let's say, it requires a much more sophisticated software infrastructure than what you would need for a simple domain decomposition scheme. But we can do it. We know today how to do it, and the software for it exists. Requires a few 10,000 lines of code, or maybe a few 10,000 lines of code to do this. Okay, so let's look at the pros and the cons. So the pros is that the convergence in an ideal case does not depend on the number of subdomains anymore. Okay, we saw that for the domain decomposition, there was a dependence on the subdomains because information only ever propagates from one subdomain to the next in one iteration. Here, we consider this a global problem, and so we can think of convergence as in one step. It's as if you solved a linear system just on one processor. We know that we can do load balancing even with additivity. We have, not we, but others have shown that you can scale this to hundreds of thousands of processors. In deal.II, we've scaled this to significantly over 10,000 processors, and it scales pretty well. I'm going to show you a few pictures later on. On the downside is you have to write a lot more sophisticated software, or maybe the better approach to this would be, of course, that you use what other people have done already. There is very powerful software for basically all of the steps. It relies by and large on iterative solvers, even though there are some parallel direct solvers that are actually pretty damn good. But most of the approaches that we use are iterative in nature. And then the big drawback, the big obstacle always is that if you have iterative solvers, you need to have preconditioners, and the preconditioners that work in parallel are very sophisticated. So I will have to come back to this at the end of this lecture. So to give you a little bit of an idea of, let's say, what are the things that you need to do if you want to implement global solvers, I'm going to just look at 3 parts of it. Namely, if you have an iterative solver, then typically you need to have matrix vector products. And in iterative solvers, you also have a dot product. So I'm going to talk about these 2 things, and then I'm going to give you, let's say, the flavor of preconditioners that we know work. So if you think about matrix vector products, like in CG, for example, so you remember that when we solve linear systems with something like conjugate gradients or GMRes, that all we really need to have is a matrix vector product. We don't, in reality, don't have to know what the individual elements of this matrix A are. But let's say I have the elements of A. Then think about what one processor needs to know to do its matrix vector product. So let's say you want to compute y equals A times x. Okay, so here's my matrix. Conceptually, I want to multiply it with a vector x, and I want to get a vector y out of it. And you remember that this problem might be, a billion for the vector x and a billion by a billion for this matrix. So this problem might be very, very large, and every processor will not be able to store the whole matrix or the whole vector, but only a part of it. So let's say processor P owns the rows in this red band of the matrix, and it owns these few elements here of the vector. And so it would like to compute the corresponding elements in this vector y here. So what does it need to know to do this? Well, you remember that a matrix vector product is essentially you take the product of the first row times the entire matrix. Well, we don't have to compute this on this particular processor because we're not interested in this particular element of the matrix. But we have to do this for every row in this red band here. So if you want to form the dot product between this first row in the red band and the whole vector, then you would have to know the entire vector, right? So in order to compute a matrix vector product, in essence, we need to get the whole vector x, or in other words, every processor needs to send their share of the vector to everyone else because everyone else needs it, okay? So that's going to be a lot of communication, and in particular, it's essentially an all-to-all communication. Everybody sends data to everybody else. Now, in reality, the matrices that we work with are actually sparse. Okay, so if I overlaid to this matrix here a sparse matrix that, in this case, it's the top left block of step 22, but it doesn't matter so much. So the point I want to make is that the matrices that we work with in the finite element method are sparse, and that means that not all of the entries are actually set. Most of these entries here and here, for example, are in fact 0. Okay? And even in the middle here, most of the entries in the middle are 0. So for Stokes in 3D, there's on the order of, let's say, 400 entries per row, but 400 out of a billion is still a pretty small number, right? So if you think about how you would do a matrix vector product in this case, remember that we need to take the dot product of the first row here with the entire vector. Okay? Well, so the elements of the vector that I need to multiply with this red block here, that should be square. So if the screen resolution comes out right on the video, then this will be a square block. Okay? So in order to do the product of these elements of my matrix with the elements of the vector, I need the elements of this vector in this block which I already own. Okay? So the parts of the vector that I need to get at are actually not all of the entries, but it's only, for this particular row, the entries that are non-zero in this row. So there's a few here, for example, okay? But then actually there's none over here. So I need a few select entries from up here, but I don't need any of those here for this first row. For the second row, it looks similar. For the last row, well, I don't need any of the ones up front, but I need some over here. So there's a few select entries down here that I need as well. So what I want to illustrate with this is that in reality, processor P, in order to compute the dot product of the rows that it owns with the vector, does not need to know the whole vector, but it really only needs to know those elements for that correspond to columns that are non-zero in its own block. Okay? And so that's the union of columns in the rows that it owns. And in particular, the majority of these entries, it will actually already know, because these are the corresponding ones that it stores. So you need to import only a relatively small number of vector entries in order to form a matrix vector product. So the elements that you need to get at are all of the elements xj for which there is a non-zero aij for a locally owned row. And if you think about it, so aij are, let's say, in the finite element methods, all of the degrees of freedom I and j that couple. So these are I and j's that sit on the same cell, right? So if xi, that's the row I that I'm looking at, if xi is a locally owned degree of freedom, that means it corresponds to one of the columns, one of the rows that I own locally. I only need to know those xj's from a vector that couple with the i's that are locally owned. That's of course, in the lingo of the previous lecture, exactly the locally relevant degrees of freedom. They live on my own cells plus the ghost cells. Okay, so all you have to import are the degrees of freedom that live on the ghost cells. And you can imagine that's a relatively small number, right? So here's a picture of this. So let's say I'm on the processor that owns all of these yellow cells here. The only degrees of freedom of x that I need to import are the ones that live on one row of cells around my own subdomain. So let's say the red ones belong to the processor that owns this one here. The green ones belong to the processor that owns that subdomain down here. So it's a relatively small number of degrees of freedom that I have to import. And the way you implement this is that up front you require which elements do I need to know. So before I even start doing a matrix vector product, I'm going to think about, okay, so these are the rows that I own. What are the degrees of freedom that I don't locally own but that couple in these rows? And then I'm going to find out, let's say, okay, so I need elements 2, 4, and 6. 7 to 20 I own. 22, 24, and 26 I need to get. So 2, 4, 6, 22, 24, 26 are the ones that I need to import. I'm going to find out who owns these. That's an operation that I can do locally. I'm going to send that processor a message, and I'm going to say, well, every time we do a matrix vector product, these are the ones that I need from you. Okay, so that's something that I do up front. And then when I do a matrix vector product, every processor sends the vector elements that other processors need to know. That's the first step. Then I do the local product. So I can do the product of my own part of the vector with this part of the matrix. Okay. And then I'm going to wait for the processors that send me these entries and these entries, and every time I get a few entries from one of the other processors, I can do the corresponding matrix vector product with these entries until I have gotten all of the the data packets from others, and I have finished doing my dot product with all of these rows and filled the right-hand side vector. Okay, so this is how we implement this, and you see that it only requires point-to-point communication. So not all to all, but every processor is going to send the elements that it owns only to those other processors that actually need it, and that is something that they have communicated up front here. So in other words, we can implement matrix vector products fairly efficiently. In particular, if we do it in this way around, that we first send data and then we do our local product. So this is something that we can do while we wait for data. That typically takes quite a significant amount of time because we have to go through all of these elements here, and that's the majority of the ones that we need. And while we do this, the data starts coming in, so we can interleave communication and computation. We can do computation while data comes in. That requires, of course, that we send data first. Okay, so that's a fairly common methodology. First send the data, do some local work, and then work with the data that comes in. Okay, so that was matrix vector product, and I showed you that that is something that we can do efficiently because it only requires point-to-point communication, and we can interleave it with actual computations. Now, let's go back to the fundamental algorithm that we often use for linear systems, namely the conjugate gradient method. So this is a copy of the Wikipedia description of the conjugate gradient method. So in particular, here's the main loop, and in every loop we have vectors R and P. We multiply the matrix A by this vector P. We form this ratio, and so on and so forth. So I already talked about this operation, A times P. Okay, that's the matrix vector product. We need to do this once in every iteration. There's a second matrix vector product, but it's with the same vector, so I'm going to store this one here in a temporary vector. So I'm going to say, let's say, Z equals AP, and then I'm going to compute this as PKT times Z, and here I'm going to use my temporary vector Z again. Okay, so there's really only one matrix vector product in every iteration. And then there's one at the very beginning if you want to. Now, what I'm going to highlight here is that there are dot products. Okay, so I need to form a dot product of a vector with itself. I need to form a dot product of pk with the temporary vector that I got out of the matrix vector product. Okay, and then there's going to be another dot product rk plus 1 times rk plus 1. In reality, so if I compute this one here, then I can reuse it in the next iteration up here. So I'm going to store that in some temporary variable. So in reality, there are only two dot products in CG, namely one here and one here. So if you think about the dot product, so I have this long vector with 1 billion unknowns, and I want to multiply it with another long vector with 1 billion unknowns. And let's say on the processor that I'm on currently, I own only these elements here. So in order to form the dot product, which is the sum over I from 1 to n, so from 1 to 1 billion xi, yi, what every processor is going to do is they're going to multiply this product, this element, with this element, and add to it this element times this element, add to it this element times this element. Okay, so every processor can do the product of the local parts of these vectors by itself. But then I need to sum up the contributions from all of these individual products of the local parts. So this is something that every processor can do by itself, but then I need to sum it up. Okay, so the way you would typically do this is, let's say everybody sends their local contribution to processor 0. Processor 0 adds it up and sends the result back to all of the other processors. Now, there's a more elegant way. Let's say if you don't want to have this global communication, let's say processor 2 would send their data to processor 1, which adds it to its own contribution. 4 sends it to 3. 6 sends it to 5. and so on and so forth. So then processor 1 has the contributions from 1 and 2, 3 has from 3 and 4, 5 has from 5 and 6. Okay, so processor 3 sends it to 1, 7 sends it to 5. Okay, so this way you only ever do point-to-point communication. You never have this bottleneck where everybody tries to send something to one processor. Okay, so you can do it like in a tree, right? That's what I just described to you, where everybody sends it to the neighbor. So I have a tree, a binary tree, for example, where everybody sends it up. Okay, these send it up, then these send it up to one processor, and so you can do it with at most 2 communications going into every processor at any given time, but you need log n steps if you have n processors. Okay, so if you do it this way, then you avoid the bottleneck, but ultimately what you need to do is you need to have a global synchronization. At one point, one processor has to add everything together and then has to somehow get it back to all of the other processors, either by sending it to everybody or by one sending it to 3, or let's say one sending it to 5, then one sending it to 3, 5 sending it to 7, then one sending it to 2, 3 to 4, 5 to 6, 7 to 8. So, right? That goes back down the tree in the opposite direction. Ultimately, there is a synchronization point in this. And if you think about, let's say, systems with a million unknowns, a million processors, this dot product turns out to be maybe the surprising bottleneck in this whole procedure. So dot products are something that are implementation-wise much easier to implement than the matrix vector product. But in reality, they're, let's say, a much more stringent bottleneck because they do require global communication. In practice, I think, let's say today in 2015, we're not there where that is the bottleneck on today's computers. You need to go to, you know, 1 million cores. Very few of us have access to 1 million cores, and I think in the foreseeable future, very few of us will have access to this. So for the next few years, the dot product is not the bottleneck of CG, but it is something that, let's say, gives you an idea of what are the conceptual difficulties to parallel computing. Okay, so the last issue that I want to address in this lecture is parallel preconditioners. So you remember that in order to compute something like, or the solution of AX equals B with a Kranov space method, if you go back to the slide with the CG method, you will find that, well, yes, we need a matrix vector product. So I give you a vector y. We need to multiply y by this operator A and assign it to z. There's a variety of vector-vector operations. So like I said, there's dot products. But there's also, you need to take a vector and add a multiple of another vector to it, okay, or subtract from it. That's basically the operations that you have to do, okay. Then, of course, if you want this to converge reasonably quickly, you need a preconditioner. Okay, a preconditioner is a matrix P, or let's say an operator P. I don't have to know the elements of it, but it is an operator that I can apply to a vector W, and I get a vector V out of it. What we want is that P approximates a to the -1. Okay, so if I have an exact a to the -1, you remember that we converge in exactly one step. So we discussed this in great length in lectures 35 to 38. The question is, in the context of parallel computations, what are the issues? What are the things that you encounter? And I'm going to show you a few ideas that turn out not to work very well. And then I'm going to just briefly touch on what everybody uses today. So think, for example, of a block diagonal preconditioner. So essentially what I wanted to show here, let's say I have subdivided this matrix in between 3 processors. And well, I drew these blocks of different size because I could. In reality, you would probably want to choose them roughly the same, but that doesn't matter so much here now. So for the purpose of discussion, the size of these blocks is not important. So let's say the yellow processor stores the rows from here to here, the red one from here to here, and the green one from here to here. And of course, they store the entire row, not just these diagonal blocks. But what we can do is, for example, we could have a preconditioner that just on every processor, you take the inverse of this block, assuming that it exists, or let's say an ILU or something. Okay, so you compute the inverse on every processor of this block, and then what you do is every time when you need to multiply your preconditioner matrix by a vector, then let's say the yellow processor stores these elements here. It's just going to multiply them with the inverse of this block. That's a local operation. Okay. The red processor is going to take these elements of the vector and multiply them with the inverse of this block, and so on and so forth. Okay, so you get an operation that we can do completely locally. We don't need any communication with this. In practice, what we often do is we don't take the inverse of a block, but we approximate the inverse of a block, let's say by an incomplete LU decomposition, or by one SSOR sweep. So it's not important that we take the exact inverse, but something that approximates the inverse. So in other words, a preconditioner for this diagonal block, for this block here. A preconditioner not for the whole matrix, but for only this block. So every processor has a preconditioner for its own block, and then the sum of these preconditioners here would be the preconditioner for the whole matrix. Okay, so it has appealing properties that we can do it locally, we can apply it, we can compute it locally, we can apply it locally. The downside is that it deteriorates if you have more and more processors, and that's relatively easy to see, because in the extreme case where every processor would store only one row of this matrix, the diagonal block is really only the diagonal element. Okay, so if you take the inverse of the diagonal element and you multiply the corresponding element of your vector with it, well, that's the Jacobi iteration. We know that Jacobi iteration is about the worst preconditioner you can think about. Okay, so diagonal block preconditioners don't work very well because they don't exchange data between processors. That's the fundamental problem. Essentially, you have something like a domain decomposition method where every processor solves something on the subdomain that it owns. Okay, so it doesn't work with large numbers of processors. You can do this in a slightly smarter way. So you remember that every processor owns the entire row of this matrix. And so what you could do is, let's say you compute the inverses of these diagonal blocks, and then we're going to do the following. So whenever you apply a preconditioner, processor 1 is going to take the elements of the vector that it owns and is going to multiply them with the inverse or an approximation of this block here. Okay, and then it's going to send the elements of this product of these elements in this block to processor 2. Okay, so processor 2 is going to form the dot product of this block and the set of vector elements that it got and puts it over on the right hand side, and then multiplies them with the inverse of this diagonal block. Okay, then processor 1 also sends these elements to processor 3, which applies them for this part of this off-diagonal block. Processor 2 sends its elements that it just computed to processor 3, which applies it to this part of its off-diagonal block. They both go to the right-hand side, and then you multiply it with the inverse or an approximation of this block. Okay, so this is the equivalent of a triangular block preconditioner. So you might remember from your basic numerical linear algebra classes, this is the equivalent of something like a Gauss-Seidel or an SOR iteration, right? Where you use knowledge of one element that you've already computed and you put them in here, bring them over to the right-hand side, and compute the next element. Okay. So again, the blocks on the diagonal, or the inverses of these blocks of my preconditioner P, can be computed locally. They can be applied locally. I can also approximate them as before for each block. I don't have to have the exact inverse. This works reasonably well as far as convergence is concerned. So it converges reasonably rapidly if you do this, because we also know that Gauss-Seidel is not a terrible preconditioner. Okay. The problem, of course, is it is sequential, right? I needed to compute first the product of the inverse of this block with these elements and then send it to processor 2, who cannot start doing its work until it has gotten this information. Okay, then it computes the inverse of this block and sends it on to processor 3, which again cannot start until processor 2 has sent the information. So, in other words, the whole process is sequential. Yes, we have a parallel computer. It might have 1,000 processors, but processor 2 needs to wait for 1, 3 needs to wait for 2, 4 needs to wait for 3. In essence, out of 1,000 processors, only 1 has something to do at any given time. That is not a useful strategy. Okay, so I mean, this doesn't scale. If I have more and more processors, it will require me more and more time to do this. So the only reason why I would ever want to apply a solver like this is because you cannot store the matrix on one processor, right? Because one processor would be exactly as fast as 1,000 processors in doing this preconditioner. So the only reason why you would ever want to do this is because you don't have enough memory on one processor. So what I want to show you is, of course, what works, right? So the previous two methods didn't work. What does work is multigrid methods. So geometric multigrid, we know, works very well for elliptic problems. If you go to lecture 36, for example, you will learn how geometric multigrid is supposed to work. Okay. What you have to think about in the parallel context is this: let's say you go from one level to the next coarser one, then you might have to communicate with other processors because the cells of the next processor may be owned by some other, the cells in the next coarser level might be owned by another processor. So if you want to do this in practice, it turns out to be a very difficult problem to load balance this, because let's say you have, in the example that I used earlier in this lecture, you have that different processors own different subdomains. It may be that this one here has been refined, so there's a hierarchy of, let's say, 20 deep, where you have refined the cells further and further. But over here, there's a much bigger subdomain with the same number of cells, but they're very coarse. Okay, so now you go to the next geometric level, where you go from the finest cells to the next coarsest cells. So then there's only 19 levels over here, and maybe the same number of cells as over here, where you're on level 9 of your refinement. Okay, but if you see the problem, if you keep going down, eventually you will end up at a problem where there is still 10 refinement levels over here and a significant number of cells, but over here I've already gone down to the coarsest cell. So this processor has only one cell left, and this one here still has a few thousand. So that leads again to imbalance. Every time you want to do something on the 10th coarsening level, this processor has a lot of work to do, whereas this one is twiddling its thumbs and has nothing to do. You cannot derive efficient algorithms for parallel computing if you cannot load balance. You always have to make sure that at every step of this process, basically every processor has something worse to do, because otherwise you have 1,000 processors, 999 out of which do nothing, and one is doing something. That's not an efficient use of your time, of the resources, of the electricity, and so on and so forth. So you need to come up with schemes that load balance. So that means that if you coarsen here and you end up with many more cells than over here, then you need to move some of the cells on level 19 to this processor over here. So you end up again with the same kind of problem as I described for load balancing with the mesh before for adaptive refinement. You need to load balance every level of that coarsening hierarchy. That turns out to be a huge problem. There are implementations that do that successfully, but it's very difficult to implement. This is very difficult to make it work in practice. So we work on this in deal.II. Timo Heiser is working on an implementation, and I think we will eventually have this. But it's a huge algorithmic challenge to make it work, and then to make it scale, so to make it work so that really every processor has the same amount of work to do at every step. So, like I say, it's possible, but it's very difficult. If you can get it to work, you will find that you can get an essentially O of n effort for the linear solver. So the overall amount of work that you have to do is proportional to the size of the linear problem as you want it to be. So it's possible to get an optimal solver out of this. The alternative to geometric multigrid is something that is called the algebraic multigrid, and I hinted at that in step 36 as well. So an algebraic multigrid essentially forgets where that problem comes from. It says, here's a matrix, and let me try to reduce this matrix to a smaller matrix, to a smaller matrix, to a smaller matrix, and at every step I'm going to approximate the solution to the original problem by the solution to the previous problem. So in the algebraic multigrid, doesn't have the problem of the mesh. It only sees the matrix, and so if every processor, for example, has 10,000 rows, then if you coarsen it, then every processor will have only, let's say, 1,000, and in the next step it will have only 100. And you achieve that by only, let's say, by always removing 90%, or whatever the fraction is, of the rows, and trying to come up with a reduction scheme. And because it's purely algebraic and is not tied to any kind of hierarchy, you can you have a much easier time to do the load balancing. It's still difficult, but it's easier to do it. Just like before, you require point-to-point communication in the smoother and probably in the construction of the multi-level hierarchy as well. You don't, in practice, get exact O of n effort, but you come pretty close to it. And the huge advantage of algebraic multigrid methods is that there are black box implementations that everybody uses for elliptic problems. So there is one implementation that is called Hyper, that is typically accessed through the PETSI library, and there's another implementation that is called ML that can be accessed through both PETSI and Trilinos. So just to give you examples of, let's say, how far you can drive this. So here's a problem where we have, that is from a paper by myself and Timo Heiser, Carsten Borstede, and Barton Kronbeckler, where we look at the problem that has 52 million unknowns. It's not a very large problem. And we solve it on a sequence of processor from 16 to 4096. Okay, so at 16 processors, every processor will store 52 million by 16, so about 3.5 million rows. Okay, whereas over here, every processor will store only a little bit more than 10,000 rows of this matrix. And what you see is that if I take more and more and more processors to solve this problem, basically all of the operations of this program, so this is essentially step 40, all of these operations take less and less and less time because every processor has less to do. So the black line is the ideal speed up. Okay, so that would mean that if I take twice as many processors, I need half the amount of time. And the one outlier that is a little bit of a problem is this red line here. That is the linear solver. Okay, so that's the CG plus M plus Hyper in this case as preconditioner. But you see that I still get, fairly reasonable speed up from, let's say, 32 to about 512 processors. This red line here indicates 100,000 elements per processor. So what you see is that, let's say, when I go beyond that point, I don't quite get the optimum speed up anymore. And that's a common observation that if you have less than 100,000 unknowns per processor, so over here, that you lose scalability. Okay, but if you have if your problem is large enough that you have more than 100,000 unknowns, you get fairly good scalability out of this. So this line here is almost parallel to the black line, right? That's what we want to see. Twice as many processors, half the time. So this is what's called strong scaling. I take the same problem and I throw more and more and more processors to it. Here's another example from a paper by Jörg Fohne, Timo Heister, and myself, where we solve elasticity problems as part of an elastoplastic contact problem. And again, you see that if the problem is small enough, less than 100,000 unknowns, so in the left half, everything scales nicely. Okay, when I get to problems that become large, so this is the perfect, the dashed line is perfect speed up. The yellowish boxes, brownish boxes here are the actual time of the solver. So if I go beyond that, then that stops working. Okay, so maybe I can say that it stops working maybe here, somewhere at, I don't know, 40 or 50,000 unknowns, I think is what we have for this problem. So this is already, I mean, a fairly sizable number of processors for a problem with only 10 million unknowns. Now let me show you the opposite, something that is called weak scaling. So in this case, I'm going to say I keep the number of degrees of freedom per core constant. So in this case, I have 1.2 million degrees of freedom per core, and I just increase the size of the problem with the size of the processors. So I start at 8 processors. Let's say I double the number of processors. That would mean I also double the size of the problem, and I get something that, well, takes a little bit more time, but not very much. Okay, so of course, if I go from 8 to 1024, I increase the size by a factor of 128, but you see that the runtime does not increase very much, maybe by a factor of 3 or so. Okay, so even though I made the problem 100 times larger, the program takes only 3 times as much time. And I mean, you have to remember that 1024 processors times 1.2 million degrees of freedom, that's a problem with more than 1 billion unknowns already. Okay, so that's, in practice, fairly good speed up if I get something that only slows down by maybe a factor of 3. So I hope what you get out of these pictures is that with this technology of algebraic preconditioners for a CG iteration, we can go to very large problems and solve them efficiently. Okay, so to sum this up, this issue of parallel solvers, the mental model that I think today most codes adopt when we solve large linear systems is that let's say when we solve PDEs that require a lot of degrees of freedom, is that we want to see the linear system as a whole. We want to see the mesh as a whole. We want to see the linear system as a whole. And then we apply a Krylov space solver like CG or GMRes to the whole linear system. And what I showed you is that, let's say, the matrix vector product in this is actually not such a huge challenge. The challenge is more to come up with preconditioners that can do this. And what everybody today uses is algebraic multigrid methods as black box preconditioners. So essentially, it's a one-line call in deal.II where you set this up. You just throw it into ML or PIT or Hyper, and it works as a preconditioner. That works for the elliptic blocks. And if you have something that is more complicated, let's say like Stokes or any other number of problems, then you would build preconditioners for the whole thing out of preconditioners for individual blocks, just like I showed you in lecture 38, where we built, for example, a preconditioner for the Stokes system from the preconditioner for the top left elliptic block, and then we just have to shuffle around some things. But that's how we build preconditioners for very large problems. I want to end this with a suggestion. So in the last few years, as sort of a dark horse, people have developed direct solvers that work in parallel. They're rather complicated, unsurprisingly, because you can't do, let's say, an elimination on one column and then move on to the next. But they turn out to be surprisingly competitive. So if you are unsure or if you just want to test the code, it might be worthwhile also trying those. Ultimately, they're not going to scale to tens of thousands of processors for most problems, but they would be worth trying out as a first step. So with this, I think it took me about twice as long as I had hoped for to go through this lecture, but I hope I gave you a little bit of an idea that explains, let's say, how we approach that problem of building solvers and preconditioners for large parallel problems when we have, let's say, a memory model like MPI. With that, I'll close this.